someone that makes me feel seasick. Oh, what a skill to have, oh, what a skill to have so many skills that make her distinctive.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. The principle of conservation of energy is especially useful in spring mass systems, so let's work out one of them. In this problem, we have the mass in the stretch position of the spring to begin with, x1, and we want to know what is the velocity at point 2 when the x2 is at certain value. So okay, let's give these values. That's 8 centimeters, so 0.08 meters, and the initial position is 0.1 meters, 10 centimeters. And we start from the rest. Just release the spring and see what happens. So in this case, we don't have a gravitational potential energy, but we do have the elastic potential energy of the spring. So we write the conservation of energy as follows. Kinetic energy at point 1 plus the elastic potential energy, and then possibly if there's some other work to be done while we're moving, and then the same quantities, kinetic energy at point 2 plus elastic potential energy at point 2 at x2. So in this case, there is no work there's no friction, for example, so we can neglect that one. And initial velocity is 0 to begin with, so that term is 0. So we are solving for the v2 only in this case. So we have these halves here in each term, so they cancel, and then we get v2 squared is just k x1 squared minus k x2 squared. And before we go on, let's think about this x1 and x2. So they are always the displacements from the rest position. So this means that we cannot select the x equals 0 arbitrarily like we do in the case of a gravitational potential energy, but we have to define the x equals 0 where the spring is unstretched. That is because at that point the gravitational or the elastic potential energy is 0 because x is 0. And in this case, we have followed this principle, so we can just go on and solve for the final velocity v2. So that's going to be squared of there's of course m involved there. So once we bring that one over to the other side, we get square root of k over m of x1 squared minus x2 squared. And let's give some values. So the spring constant in this case is 5 newtons per meter. It means 5 newtons of force to stretch it 1 meter. And the mass of the spring, as we see, that's already there, 0.2 kg. So we can put the values in. 5 newtons per meter divided by 0.2 kg. And first displacement or initial displacement 0.1 meters squared minus the point of interest 8 centimeters and from square root we get, of course, plus minus 0.3 meters per second. So which one do we pick? In this case, the both values have a physical meaning. The -1 corresponds to the case when the box is going to the left, the situation we have depicted here. But when the box moves all the way to the other end and gets rebounded by the spring, it will come to this very same point at 8 centimeters, and in that case its velocity is to the right. So that corresponds to the positive one. So, but to be strict, we wanted the value when it's on its way to the left, so we exclude that one and we just pick the negative one from here.
Bridges.